Have you ever wondered what everything is really made of? I mean, everything you can see, everything you touch, even you. It's all built from these impossibly tiny little blocks. So today, we're going to go on a journey to find them. We're going to explore the unseen world of atoms and molecules.
Okay, so here's the game plan. We'll start with a question that people were asking thousands of years ago. Then we'll see how scientists figured out the rules these tiny particles play by. After that, we'll look at the first real theory that put it all together. Then we'll see how they team up to build everything around us. And finally, we'll try to get our heads around just how incredibly small and light they are.
All right, let's start at the very beginning. And this story doesn't begin in some high-tech lab. Nope. It starts in the minds of ancient philosophers who were wrestling with a really simple but massive question. If you keep cutting something in half, do you ever get to a piece you can't cut anymore?
And what's really wild is that people all over the world came to the same conclusion, completely on their own. Way back around 500 BC in India, you had the idea of parmanu, an indivisible particle. Then, about a century later in Greece, thinkers like Democritus were talking about atomos, which literally means uncuttable. It's just amazing, right? It shows this deep human need to understand what our world is fundamentally made of.
So you've got these two different names from two totally different cultures. But check it out. The core idea is exactly the same. The belief was that if you just keep dividing matter, you eventually hit a wall. You get to a final, fundamental piece that you just can't break down any further. But for thousands of years, that's all it was. Just a cool idea, a philosophical concept with zero proof. Okay, so philosophy is great, but to turn this idea into actual science, we needed rules. We had to figure out the universal laws that explain how these tiny, invisible particles actually behave and interact with each other.
The first huge breakthrough is this one, the law of conservation of mass. And it's such a powerful idea. It basically says you can't just make matter appear out of thin air, and you can't make it disappear either. When a chemical reaction happens, all the stuff you started with is still there. It's just been rearranged.
Yeah, it's kind of like baking, right? If you put 4 grams of hydrogen and 32 grams of oxygen into your oven, you're going to get exactly 36 grams of water out. Nothing gets lost, nothing is created, the math always adds up.
And then there's the second crucial rule. This one is all about consistency. It says that a pure compound, something like water, always follows the exact same recipe. It doesn't matter if you scoop it out of the ocean, get it from a tap, or make it in a lab. The recipe is fixed.
And Miss Chart just lays it out so perfectly, doesn't it? Whether you've got a little bit of water or a whole lot of it, the weight ratio of hydrogen to oxygen is always 1:8. This was a massive clue. It strongly suggested that matter wasn't just some random goo, but was made of distinct little pieces that combine in very specific, predictable ways.
All right, so we've got these two huge clues. Matter is conserved, and compounds have these fixed, unchangeable recipes. The stage was perfectly set for someone to come along and finally connect all the dots with the first real scientific theory of the atom.
And that someone was John Dalton. His atomic theory was a total game changer. He proposed that, yes, everything is made of tiny atoms. He said they're indivisible, and they just combine in simple ratios. Now, why was this so revolutionary? Because his theory was the aha moment. It perfectly explained why those two laws we just talked about actually work. Conservation of mass? That's just atoms getting shuffled around. The fixed ratios? Well, that's just atoms combining in simple pairs, like 1:1 or 2:1. It all made sense. But, that's the beautiful thing about science, right? It's not about being right forever. It's about building on what came before. We know now that Dalton didn't have it 100% correct. Atoms aren't indivisible. They're made of even smaller things, protons, neutrons, and electrons. And we also know that atoms of the same element aren't all identical twins. Some can have a few extra neutrons, which makes them a bit heavier. We call those isotopes. So now we have these fundamental building blocks, these atoms, and we have the rules they play by. So what's next? Well, what happens when they start teaming up and forming little groups?
They form something we call a molecule. And it turns out most atoms are pretty social. They don't really like being alone. They prefer to exist in these little groups, all chemically bonded together. And that group, that little team of atoms acting as a single unit, that's a molecule.
Okay, and this is a really key distinction. When atoms of the same kind hook up, they form a molecule of an element. A perfect example is the oxygen we're all breathing right now, O2. It's just two oxygen atoms stuck together. But when atoms of different kinds get together,
They form a molecule of a compound. Think about water, H2O. That's a team made up of 2 hydrogen atoms and 1 oxygen atom. Okay, so let's talk about scale. We know these things are the basis of everything, but honestly, this is where our brains can kind of short-circuit. It's almost impossible to truly grasp just how mind-bogglingly tiny we're talking about.
Just look at that number. 10 to the negative 10 meters. That's about how big a single hydrogen atom is. It's a scale so small that our everyday words like meters or even millimeters become completely useless. They just don't mean anything anymore.
So to even try to get a handle on this, picture an ant. You can see an ant, right? Now imagine something 10 million times smaller than that ant. That's the scale we're on. It's just truly staggering.
So, obviously, trying to weigh these things in grams would be a nightmare of decimal points. So scientists did something really smart. They just invented a whole new scale just for atoms. It's called the atomic mass unit, or U for short. They picked a common atom, carbon-12, and said, okay, this is our benchmark. They defined 1U as exactly 1/12 the mass of that single carbon atom. And using this system, everything suddenly clicks into place. It makes comparing atoms super easy. We can see that a hydrogen atom is about 1U. An oxygen atom is about 16U. So right away, we know that oxygen is roughly 16 times heavier than hydrogen. And that is exactly the kind of info you need to understand those chemical recipes we were talking about earlier.
So, we've gone from an ancient philosophical guess all the way to a precise science that has literally built the modern world. Our understanding of the atom has given us everything from new medicines to the computer you might be watching this on. And it really just leaves us with one final exciting question. Now that we understand the building blocks, what are we going to build with them next